it's a pleasure to introduce Vincent from Birmingham, who visited us today, and he's a senior lecturer in Birmingham University, and he's going to talk today about the design and verification of time-critical Byzantine fault tolerant systems, which I think is also.
That's great.
Oh.
Or should we all watch on YouTube?
We can do that as well. It's the HDMI.
Sound solution.
You didn't have to come. You can just watch the talk on one.
HDMI.
More nerdy if everybody is sitting in the same room watching the same YouTube stream. What's the speaker being in the same room?
Oh, now screen sharing is disabled.
Maybe.
Let me try again.
I mean, the other solution really is log in the
Touchy.
Electron PC and just start the YouTube.
That would also be. No, we want the laptop.
You cannot connect to that. Right. The project is a member of a Zoom room.
Not PC.
Yeah,
Touch the display. I'm sure. Give me a second. Laptop. Now it should work. Yes. So and now you can try to screencast.
Yeah, I think I'm sharing my.
You're
screen
sharing.
now. Yeah.
So this one should work as well. Yeah, I think that's all. Okay, let's try again. Welcome, Vincent, from University of Birmingham. Thanks for visiting us today. And Vincent is a senior lecturer in Birmingham, and he's going to talk about design and verification of time-critical Byzantine fault tolerant systems, which I think is also the title. Is it the title of your new investigator? Yeah, Vincent also just got his new investigator. Well, how long is it? 1 year?
Yeah.
New investigator award accepted. So congratulations, and we are looking for your talk.
Right. So when I was preparing the presentation, I wasn't sure whether there would be more security people, more theoretical. I think we have a mix generally of security and more formal methods people here. Is that the case? Yeah. Okay. So, but the talk is I'm gonna stay at a high level, and feel free to just ask me for more details if you want to know more about a specific topic. I'm gonna talk about a bunch of work that we did with some colleagues, and in particular with my good friend and colleague Jeremy Becouchard from Exeter, David from LB Research, and Junction from Monash University. And also more recently with Sam and Rahli, who are both at the University of Birmingham. And yes, it's on the design verification of distributed systems, in particular Byzantine fault tolerant distributed systems. If you haven't heard about that term, Byzantine, I'm going to talk about what this is. And time critical, which is quite vague, but I'm going to mention what I mean by that. So let's see, I think I can hide this somehow, right? Yeah. No. I'll move it out of the way. So this is all about distributed systems. And why do we care about distributed systems? Because nowadays they're everywhere. Why do we use distributed systems? For better performance, for resilience. So that's the main point I'm going to be discussing here. We have a service and we want to make it resilient. We're going to distribute the service across several machines so that if one goes down, the machines are still there to run the service. More storage as well. So we use distributed systems to have, for example, distributed databases and do sharding, maintain different bits and pieces of the database on different computers. But if we do this, when we use distributed systems compared to just one machine, that brings in complicated problems, new problems, distributed problems. So for example, if we have several machines that are supposed to do something, an action with each other, discussing with each other and trying to do some action as a group, then sometimes they have to do something like this consensus, they have to reach consensus on what the action should be. We have 4 computers, 2 want to do an action A, 2 want to do an action B. What do we do? They have to reach consensus. Broadcast is also a typical problem that we want to solve. One of the computers is going to broadcast, send a message. We want to make sure that everyone is going to be on the same page and will receive the message. So we have those problems that we are trying to solve to make those distributed systems work. And we want them to achieve some properties. So the typical properties that we want them to achieve are liveness and safety properties, validity and agreement. So we want them to do eventually something. So validity, liveness, and we want the behavior of those distributed systems to be safe. To, for example, reach agreement, that's a safety property. And also, those distributed systems, they run in different kinds of environments. We have different kinds of systems out there that run in different kinds of environments. If, for example, some of them will be running in one data center where the communication is bounded, so we're going to have synchronous systems when we know how long it takes from one message to go from one machine to the other. Or we have distributed systems that run across the world, and there it's not quite always clear how long the messages will take to go from one machine to another. So we talk about asynchronous systems because there is no bound in the transmission delays. And we have models in between that assume some sort of eventual synchrony. Eventually the system is going to be synchronous, that's partial synchrony. So distributed systems are out there, they're interesting, they bring in some challenges. We want them to achieve some good properties in different models. How do we do this? So in particular, the kind of distributed systems that my colleagues and myself are interested in are fault-tolerant distributed systems. So we have, and especially those BFT-SMR, that means Byzantine Fault Tolerant State Machine Replication. So what does that mean? It means that we have a service, think about any service, banking service, for example, and we want to make the service resilient so that if the service goes down, it's still available somehow. So how do we do this? One way we can do that is replicate the service across different computers so that if one of the computers goes down or is attacked, then the service is still available to the other machines. But then one thing that we want to achieve is that if you check your balance on using one of the computers, then you're going to get the same balance as if you were using the other computer. So how do we do this? That's what those BFT-SMR protocols do. They ensure that the machines stay consistent with each other so that your balance is the same essentially on all the computers. And this is what is used nowadays in some of the blockchain, the blockchains out there, such as, for example, in Hyperledger or Tendermint. They use those or variants of those BFT-SMR protocols to make sure that your blockchain, so the blockchain is a distributed ledger, to make sure that your ledger, the distributed ledger, is the same everywhere. There are many mechanisms that are used to achieve this. BFT-SMR is one of them. So this is nice and well. We know how to implement BFT-SMR protocols to reach consensus. That works, but not quite, because we know this good old FLP theorem from 1985, which says that actually we can't do that. Or at least in some scenarios, we cannot do that. We cannot always reach consensus. So what's happening here? We have in asynchronous networks, the issue that if we have at least one fail-stop process, so if at least one of the nodes can go down, then we have the issue that we cannot reach consensus. The consensus protocol is not going to terminate. We can't have a consensus protocol that terminates. That's just not possible. And the proof is very simple. The proof essentially plays around with the messages to delay them enough so that the nodes will never make progress and will never reach consensus. So how do people get around this? There are two main techniques to get around that: randomness and partial synchrony. And the one that I'm going to especially focus on is partial synchrony. So the protocols that we deal with are still deterministic, that they don't have any notion of randomness. And this partial synchrony is something in between synchronous and asynchronous. So you have an asynchronous system, but you have the guarantee that eventually, at some unknown time, the network will become synchronous. So that's one definition. There are many equivalent definitions. If you don't quite know about the literature there's another definition that's sort of sometimes a bit more intuitive, which is that you have those sequences of time periods. Some of them are synchronous, some of them are asynchronous, but you never know whether you're in a synchronous or asynchronous time period. Is that something that you're all familiar with already? Am I just repeating stuff that you already know? A bit?
I'm not familiar.
You're not familiar, thank you. Yeah. Okay. So I'm laying the foundations of what we're doing. So sorry if some of you are already familiar with this, but sort of so that we're all on the same page eventually to talk about what we've been doing in that area. So we're happy with those distributed systems, the DLTSMR protocols, not quite, we have this FLP, but we know how to solve the issue. We just assume partial synchrony. It's a reasonable assumption to make those good, bad periods. But then comes the other issue is that typically those protocols I should probably not use this one because this is me shooting myself in the foot, but you'll see that actually this is not quite right. But anyway, so there is this joke that those protocols are expensive because typically they work like this. You have a bunch of servers and you have one node sending messages to the others, and then they're all going to reply to each other, and then they keep doing this, and then they send lots of messages around. This is just a joke. It doesn't really work like this, as we're going to see, but it's kind of true that typically those protocols work in phases like this, where they send a lot of messages around. So that's something that people have been addressing over the years, trying to limit the number of messages being sent so that we don't use up all the bandwidth. We keep a reasonable bandwidth. And they're also error prone. They rely on complex sort of synchronization protocols to make sure that all the nodes are on the same page. And those protocols are kind of complicated. There are lots of corner cases because we have nodes that can be malicious and try to abuse the system. And so, and how can they do that? There are lots of corner cases to consider. And people, even recently, 2017, considering the history of BFDSMR, 2017 is still quite recent. People have still managed to find issues in protocols. So, for example, ZZIBA is a protocol that is a very important protocol in the area, and people found some safety issues with this protocol, which they managed to fix eventually. So again, we have those BFDSMR protocols. They have issues, they're expensive, they're complicated, but that's what people have been addressing over the years. So this is a bit of a history of the field. It sort of started as with everything in distributed systems with Lamport. Everything started from Lamport. And so this SM protocol from 82 is one of the first BFT protocol, Byzantine Fault Tolerant protocol, and it stands for signed messages. It was a synchronous protocol, but that sort of started the field there. And then people have been trying to relax the assumptions and to make them more applicable, more usable. So PBFT came quite a few years after. That was the first practical BFT protocol. PBFT stands for Practical Byzantine Fault Tolerance. And that was also the first practical asynchronous protocol. So relaxing the assumption that we know how long the messages take to arrive from one place to go from one place to the other place. Okay, something I didn't explain is Byzantine, in case you don't know what that means. So this is something that Lamport came up with, obviously. And that means that we have a fault model where the nodes can act in a Byzantine way, meaning that they can have some arbitrary behavior. So they can crash, they can lie, they can abuse the system in any possible way. So that's what we mean by Byzantine. Byzantine fault tolerance means that we're able to tolerate any kind of fault, even not just crashes, but also malicious participants. After that came some interesting protocols, A2M and MinDFT, that use this concept of hybridization. What is that? It means that those the processes rely on some trusted components. So on TPM, IntelliSGX, you can use those components that are trusted and allow you to run some code that cannot be tampered with. So even if you have a node that runs some code and can act maliciously, at least they cannot tamper with this bit of code. And what they did, for example, and we're going to go back to that with MinDFT, and it was to show that it's enough to have a trusted counter to reduce the complexity of those protocols quite a lot, actually. Then after that, people focused on efficiency quite a bit. So BFT Smart was the first practical implementation of BFT, essentially of a variant of PBFT. COP was a parallel version of PBFT-like protocol, and then started this line of work, the streamline protocol, and we're going to get back to that later, which simplifies the message pattern of those protocols. So they or the structure of those protocols. So the protocols before that were relying on this pattern of having a normal case operation and what we call a view change. If something is not working correctly, we're going to change the view. We're going to change what we call the leader. But I'm going to get back to that. This is something that led to complicated structures for those protocols, and that changed starting from hot stuff, where they used a different pattern, and that led to those streamlined BFT protocols. But again, I'm going to go back to that in a minute. And building on top of those protocols, after that, we've seen an explosion of protocols that build on top of hot stuff or even PBFT still. So feel free to also interrupt me if you have any question regarding this. I've got about 30 slides. I don't have to go through the slides, but that's where we're going to reach eventually. Maybe we don't have to. Right, so PBFT was the first practical protocol. And so this is how it works. So we have 3F+1 replicas so that we can tolerate F faults. So that means that to be able to tolerate one faulty node, we need 4 replicas. And so here we have 4 replicas. That means that if one acts maliciously or crashes, then the system is still going to run. The system is still going to provide the service that it's supposed to provide. Again, this is a layer that you apply on top of any deterministic service to make sure that the service still works, even though one machine, in this case, goes down. And so the way it works is that the nodes will receive requests. You have a distinguished node called the leader, who's going to drive the requests and make sure that they're accepted by enough nodes to be guaranteed that all the nodes will be on the same page and will maintain the same ledger, if you want to think about the ledger, or the same state of the service. So the leader is going to send those pre-paper messages, and then you see this sort of message pattern that we showed before, but not quite as dramatic as the one we saw before, where everyone is going to reply is going to vote with those pre-paper messages, and then there's another series of votes. That's the commit phase here, and we're going to go back in a minute to why we have this. So that's the normal case operation. That's what happens when the system works fine. You have the request. The leader sends a prepare message. We have those votes prepare, those commit votes, and at the end here we can execute the command that was sent by the leader. So we have those commands. It can be an update to a state, and so here we know that we can indeed update the state, and we reply. So if the requests come from clients, we can reply to the client saying, yes, you asked me to add 10 pounds to my bank account. Here's the new balance. So this is the normal case operation. If something is not working quite well, if we see that we're not executing the requests if we see that we're not executing the requests, then the nodes will start voting for a new leader, and we'll switch leader. And this is when we run those view change protocols, those complex view change protocols that will elect a new leader, and then the new leader will make sure that it starts in a correct state and take over the previous leader. I'm not going to show what those view change protocols do, but again, you have a series of messages like this to make sure that the new leader is starting from the correct state. So in all those protocols, those BFT protocols, you always have this pattern of you send messages once, you send messages twice. And so why do we do this? Roughly, this is what's happening. So here we have 3f+1 replicas, 4, where we have f equals 1 here. And the leader will send a pre-prepared message to the nodes, and the nodes will reply, will vote, and then they will wait for a quorum of votes. And a quorum here is a collection of 2f+1 messages, so 3f+1 minus f. So in this case, if, for example, this node received 1 vote here, its own vote and a 3rd vote, that's a quorum. But this node, this replica, cannot execute, even though it has received a quorum of votes for this command. So why is that? The problem is that there could be network issues, and it could be that if this node was to execute this command, the other nodes wouldn't execute the commands, would vote for a new leader, and the new leader wouldn't get enough information to know that this replica executed the command and would start voting for a conflicting command that would clash with this one. So if you think of a blockchain, for example, we want to have a chain of blocks, and it could be if this node wasn't running if the nodes were not running the commit phase, it could be that this node accepted a block, and then the leader here is going to fork and accept a conflicting block. And that's not something that we desire with those protocols. So this is why we need another phase of voting to ensure that this doesn't happen. So this was PDFT in a nutshell. And after that came this line of work on streamlined protocols, streamlined DFT protocols that try to simplify the pattern that those protocols use. The fact that those BFT-like protocols use this normal case operation, and if the leader is detected, or if the other nodes think that the leader is malicious, then they would elect a new leader. So to avoid this complex structure of the protocols, they came up with this streamlined version where we have a unified propose vote paradigm where the nodes will send their state to the leader. The leader will make a proposal to the nodes. They will all reply to the leader. And the pattern is always the same. The leader distributes the information to the nodes, and the nodes distribute the information, reply to the leader, which then distribute the information, and so on. So what's the difference with before? Now we have here we had a quadratic number of messages, as opposed to here where we have a linear number of messages. So we have less messages, but one thing that happens here is with hot stuff is that we have an additional phase, and we'll see in a minute what's happening with this. Another thing also to mention with hot stuff is that they got rid of the view change protocol. So there's only this normal case operator, normal case operation, which integrates the view change. So the way it works is that the nodes will send a message to the leader, they will do their voting, they will decide, and eventually here it's going to go back, and the nodes will again send their votes to the next replica, which will act as a leader, and it will keep going and so on, and it will rotate through the leaders, so that if there is a malicious leader, then the malicious leader can only harm the system only so often, and eventually it's going to be detected, and the leader, the faulty node will be replaced.
Is the leader static?
No, so we start with this node as the leader. They vote on one proposal, they decide, and then here they do again a new view where they're going to consider this node as the leader. So now the node, the next view, this node is going to be the leader. They vote on this request. Next request, this node is going to be the leader, and so on. So they cycle through the leaders, through the replicas. And if you see that one of the replicas is not working correctly, then you would take it out of the system and replace it with a new node. So throughout this execution, they collect, the nodes collect what we call certificates that some action has happened. And so here at this point, we know that the message was prepared, and here we know that the message was committed or locked. And I'm going to go back to this in a minute. So we have, as opposed to PBFT, where we had pre-prepare, prepare, commit. Here we have one more phase. We have this pre-commit phase, which wasn't there before. And why is that? Because as they noted, when the authors worked on hot stuff, is that if you don't have this additional phase, you run into a liveness issue. And that's essentially the liveness issue here that they found, is that if we have a malicious participant, and so here we're voting on blocks. So we're trying to come up with a chain of blocks. And so we have block one, which is voted upon. And the nodes will vote on blocks. And once they have voted enough on the block, they will commit to this block. They will lock this block. That means that next iteration, next view, they won't vote for another block because they committed to this block. So what could happen then is that this node will vote for this block, and the malicious participant will get this node 0 to lock this block right before all the other nodes think that the system is not working properly and it's time to change view and time to change the leader. And so this node is locked. Next iteration, this node 0 won't participate in this vote where this leader is voting for this block B2 that extends also this block B, but is conflicting with B1. So 0 is not going to vote on this because it's a conflicting block. And again, the malicious node here is going to get this node to lock this block so that it won't participate in the next one. Next iteration, there is some progress that has been made. This node here can detect this, will vote again, but on the extension of this block here, and we repeat this pattern. And so here we're never extending one single chain, and we're never making any progress. We're never accepting any of the blocks actually. And so that's a liveness issue because they're trying to elect this one, it doesn't work. Trying to elect this one, which is conflicting, doesn't work. Trying to elect this one, which extends this one, doesn't work. And they keep going with this pattern forever and never actually execute any of the blocks. And so it was solved by adding another phase of voting. As always, with those protocols, you add another phase of voting, and that solves all your issues. Right, so then after that came, actually before that came those hybrid protocols. And as I mentioned, they rely on those trusted components to do some very simple actions, very simple computations that we know cannot be tampered with, and that's enough to simplify the protocol. So here, this is a version of PBFT that relies on trusted message counters. Every time you send a message, you're going to sign your message to this trusted component. And that means that, and the messages will be counted. That means that when you send your message to another node, the other node will know for sure that this is your first message, your second message, your third message. So if they receive your first message and your third message, they know that they're missing your second message. And maybe the second message was when you were trying to lie. So they will wait for your second message to see what before they can do something with your third message. And that's enough to reduce the complexity of PBFT by quite a bit, removing one phase altogether, and also having only 2 F+1 replicas instead of 3 F+1, which is a lot of nodes if F is big. So how can you implement those trusted message counters? For example, with Intel SGX, you get the guarantee that all the messages can be counted by all the participants. Yeah.
But it's not only the counter that, so the whole message needs to be signed with a counter.
Yeah.
Because
Exactly.
otherwise I can do replay attacks.
Exactly.
Like.
So what you do is that you give your message to the trusted message counter, and it appends the counter to the message, sign the whole thing, and that gives you a certificate that this message has this counter.
Yeah, the important part is there needs to be some proof of timeliness or norms or a timestamp in it that I sign.
Only the counter is necessary. That's the only thing that you need. And the counter is going to be incremented by the trusted component. The trusted component is going to, you give it your message. The trusted component has the counter 0. It appends the counter to your message, signs that. That's your first message. Then, and it increments the counter.
Yeah, but that message needs to have some thing in there that allows the leader to check that the message is fresh. Because otherwise I could generate a bunch of messages ahead and
you can generate, you can use your counter however you want. The guarantee that you get is that you can use your counter 10 times while you're supposed to use it once, but what you will generate is 10 messages with the counter 0, 1, 2, up to 9. And that means that those are the 10 messages that you actually produced and that you will be sending. And that's enough to
okay.
yeah. So it's a very simple trusted component that can be implemented in TPMs in very simple trusted environments. And that's enough to reduce the complexity of those protocols.
So every outgoing message needs automatically to go through this thing.
Yeah, and so you generate them with your trusted component, and you also verify them with your trusted component. So if I get your message, then I'm going to verify it, and this is going to tell me like, yes, it was generated by your trusted component, because those trusted components, they have their own keys, okay, that are confidential and cannot be shared with the rest of the system. Yes.
So I cannot send anything which is not going through the trusted.
You could, but then I'm going to reject your message because
Okay.
it didn't go through the trusted component.
So you essentially rely on the fact that your TPM module essentially is a member of a PKI that Intel and AMD set up when, or the motherboard manufacturer sets up.
Yeah, or I mean, if you use something like SGX, then you can get SGX to generate a key and then run some attestation to make sure that the other nodes are actually doing the same thing.
Which are very complicated protocols
Yeah.
itself.
Yeah, it's a separate problem, but yes, indeed, they're complicated protocols as well. Yeah, and very interesting. Yeah.
Right. So now the question is, we have those streamlined protocols, very nice and simple and efficient. We have those hybrid protocols, mean BFT, again, very nice and simple. Can we combine the two? Can we get streamlined and hybrid protocols? In particular, can we use on something like trusted counters to do the same thing, to simplify hard stuff, which is a 3F+1, 3 core phases protocol, into a 2 core phases, 2F+1 replicas protocol, using the same mechanism? And the answer is no, not with those simple trust counters. Why is that? In a nutshell, the pattern of messages with hard stuff is that the messages go through the leader and they will be sent, the leader will send messages to the replicas, back to the leader and so on. So that means that the nodes between themselves don't communicate. So I don't know if you're one of the replicas, I'm one of the replicas, you're another replica. I don't know what you send. I only know what the leader sends. And so because of this, I don't know if you lied about one of your messages because I don't know what's your first message, what's your second message, what's your third message. And because of this, we cannot rely on those trusted counters with those streamlined protocols.
So what do we do?
So that's some work that we did recently with my colleagues. It was this Dionysus protocol, which is hard stuff plus 2 trust components, a checker and an accumulator. But the checker component is essentially a beefed up message counter, and the accumulator is a trusted component which is used to make sure that the leader is not lying about the information it's sending.
And I'm going to mention, I'm going to go back to that in a minute.
So this is the model that we have now. We have two F+1 nodes. We have up to F40 nodes. All of them are equipped with a trusted component that can that can be authenticated, that can hash, sign, and verify messages, and that can store a bit of data. We have reliable asynchronous communication, so we know that if we send a message, eventually the message is going to be received, but we don't have any guarantee as to when the message is going to be received. And we assume partial synchrony for liveness. So asynchrony is fine for safety. For liveness, as we mentioned, because of FLP, we need to assume partial synchrony. All right, so we have hot stuff. We want to simplify hot stuff with trusted components. We know that we cannot just use trusted counters. What can we do? So there are a few places where we can try and do something. One thing that the nodes all do at the beginning is that they sort of send their current state to the leader. And the leader is going to say, oh, that's the latest block that you know about. Let's extend this new block let's extend your block with this new block and propose a new block. So all the nodes send their current blocks, and the leader is going to extend the highest of those blocks with a new block. But this relies on the fact that the nodes will send their latest blocks. So you're not trying to lie and say that you're actually working on this block while in fact you're working on this extension of the block. So that's one thing that maybe we can try and address, force the replicas to send their latest blocks. And another thing that happens here in those protocols is that the leader has to pick the highest block it received and pick that one to extend this block with a new block. And that's going to be the new proposal. So, but the leader could actually lie and extend an older block and do some sort of replay attack where it's going to or fork the chain and vote for a conflicting block. So that's something that maybe we can also tackle. This an implication of the fact that the leader can lie about the latest block it received has this implication that we mentioned this liveness issue that requires a new phase, which is called the hidden lock problem. That's the liveness issue that is there and requires another phase in hot stuff. So those two points. Those 2 points is what we addressed with those trusted components, the checker, what we call the checker, and the accumulator, forcing the replicas to send their latest blocks and forcing the leader to pick the highest block as the block it will extend. So the checker is there to improve the resilience. It's the component that allows us to go from 3 F+1 nodes to 2 F+1 nodes. And the accumulator is there to improve the performance. It allows going for 3 core phases, 2 core phases. The checker is, as we mentioned, a beefed up counter, message counter, that also stores a bit of information about the latest blocks that you've prepared. So to prepare a block in Dionysus, you need to do that through your trusted component, and the trusted component is going to store this information. And when you send your latest block to the leader, it has to be done through the trusted component. So you cannot lie about the latest block you prepared. So the one consequence is that the leader can only prepare 1 block per view. And also the replicas cannot lie about the latest blocks they've prepared. And then the other component is the accumulator. The other point that we want to tackle is make sure that the leader doesn't lie about the block it's extending. And so here, what we do is that when the leader receives all those blocks, selects one to extend, then it has to do that through a trusted component. And so then the other nodes can check that, yes, indeed, the leader picked the highest block to extend with its own block. And thanks to that, we can get rid of 1 phase.
That's yeah, right. So that's how Damisus in a nutshell. Then we typically in those with those systems, you come up with some good idea of how to improve performance, but you also want to check that indeed it improves the performance. So obviously we did some evaluation. The red line, so this is computing evaluating the throughput of the system. The red line is Damisus. The black line is a version of hot stuff, a re-implementation of hot stuff, because they have lots of optimizations in hot stuff that that we didn't want to compare against. And Damisus A is Damisus with just the accumulator. Damisus C is Damisus with just the checker, and the red line is Damisus with the two components, the accumulator and the checker. And we could report that we have some very good gains in terms of throughput and latency.
What is chained down?
Right, so hot stuff comes in two versions. There is this chain version, which instead of waiting for those 3 or 4 phases before you vote for the next block, then you start voting for the first block in one phase, and then the second phase you already start voting for the next block. So you pipeline the votes. That's the chain, the pipeline version, and we have a chain version of Damisus. Okay. So those were all implemented in C++ using Intel SGX, and the deployments were all done using AWS. Right. So
did you also verify them, the correctness of your protocol?
no, not this one. So that's what I'm going to talk a bit about now. But this one wasn't verified formally, Damisus. So that's something that we would like to do as part of this project. But that hasn't been done yet. We haven't started on the verification of this one yet, as opposed to switching gears, as opposed to this one, where so we're in this project with my colleagues. We're interested in those protocols that are efficient and also provide timing guarantees. So this is the work that I'm going to talk a bit about now. Providing timing guarantees. It's well and good to know that your system is going to do something eventually. What's interesting to know is when it's actually going to do that thing. And it's critical for some safety critical systems. For example, if you ever want to use something like this, like a BFDSMR protocol in a SCADA system, you need to know that the decision is going to be done within some before some deadline. Otherwise, your system is not going to be safe anymore. So here we're interested in cyber physical systems, which come with their own issues. So they have real-time constraints. Also, the models are a bit more complicated because you have heterogeneous systems with different kinds of components. The communication infrastructures used are also different. So that brings the systems bring their own difficulties. So here we're interested in what's below here is real-time Byzantine reliable broadcast protocols. So we're interested in broadcasting a message. So as a sender, if I send a message, I want to make sure that all the correct nodes will receive my message. So you have sensors that send some data to some devices, and you want to make sure that the devices will all be aware of that message eventually.
Sorry, you said all the correct nodes receive the message. Do you mean all the correct message is received by all the nodes?
All the correct nodes, in the sense that, again, we might have 40 devices in there, a 40 node, and we don't care about what this message does, what this node does. So as long as this sensor is correct and sending some data, we want to make sure that the correct nodes will get the data. We don't care about the 40 nodes. We don't have any control over these 40 nodes. But what matters is that all the correct nodes will get the information and will do something with this information. For example, reach consensus on some action that they want to do based on this data. Okay. I get thirsty. So this, again, this is a very old field. reliable broadcast, Byzantine reliable broadcast. And that's this is the BRB, Byzantine reliable broadcast abstraction. It's a collection of properties that you want those protocols to satisfy. So validity, this is your liveness property. It says that if the message is broadcast by a correct node, then it's eventually going to be delivered by a correct node. Notification means that you're not going to deliver two messages, a message more than once. Sorry. Integrity means that if a message is received by a correct node, is delivered by a correct node, then the message was indeed sent by a correct node. And agreement is your main safety property. It means that if a correct node delivers a message, then all the other correct nodes will also eventually deliver the message. So here we have a similar model where we have again 3f+1 nodes. F of them can be 40. In addition to that, we would like to have those timing guarantees. It's not enough to know that eventually the message will be received. We want to know when the message will be received. We want to have this constraint that says that if a message is broadcast at time t, then all the correct nodes by a correct node, then all the correct nodes will deliver the message, will receive the message, deliver the message by time t plus some bound delta RD. So that's what we want to achieve on top of those traditional BRB, Byzantine Reliable Broadcast protocols. And in addition, we want to have more realistic models. And in particular, here we're focusing on what are called probabilistically synchronous models that assume that the links are reliable and synchronous with high probability, which is true in many systems. In many systems, you can assume that, sure, eventually your message is going to be received within 10 milliseconds, but sometimes it happens that there will be some disruptions and your message is going to be received within 11 milliseconds. And that's a more realistic assumption about the networks. So those protocols, they again work in a similar fashion. Send a message once, twice. After that, you have enough knowledge about the other nodes that you can make a decision. So the way it works is that you have a node sending a message, broadcasting a message, then all the replicas will echo the message. Once you received enough echo messages, you can deliver, and then you can start this other phase of delivering the message to help the other nodes who haven't received your message yet. It's the variant of BRCA's Byzantine Reliable Broadcast Protocol, which doesn't work exactly like this, but it has similar phases. And we're finishing at past, yeah?
Yeah.
Good. That's, yeah. We're going to finish at past. So pistis is that. Pistis is a real-time Byzantine reliable broadcast protocol that achieves timeliness. And how do we do this? So we have this echo phase and this deliver phase. So we run the echo phase for some time, up to some time t. And the way it works is that we repeat the sending of our message. We're going to send it once, send it twice, send it a number of times until we get enough information that our message has been echoed. And after that, we start the deliver phase, which we run for this time period, this 2t time period, twice the length of an echo phase for a good reason, but we're going to go back to in a minute. So we keep on repeating, sending messages. The way it works in pistis is that we don't send to all the nodes, we send to a subset of the nodes so that we don't overflow the system with messages and to avoid too many messages. And if a node sends its message, echoes the message, but doesn't receive enough replies by this bound T, then it's going to become passive, because that means that the node is not safe in the sense that the node is not timely. So you don't want, say, timeliness is a safety property in the system, and a timely node is not safe. So in that case, it's going to stop participating and it's going to become passive. And we're going to try and fix the issue, and the node can come back. So this is pushing messages. We're pushing the messages to the other nodes. If we get enough replies from the other node by some deadline, fine. If not, we become passive.
And that allows transforming this turning this probabilistic synchronous model into a synchronous model, because the nodes that are not synchronous will become faulty, will become passive. The other component that's critical in this protocol, it's essentially again broadcast protocol with this pooling mechanism and this pushing mechanism, and this pooling mechanism. The other one is this pooling mechanism where you're a node, you want to make sure that you get the information on time, so you're going to pool the information from the other nodes using what we call the proof of connectivity component. You're going to keep sending messages to pull the information from the other nodes, and if by some deadline you don't receive replies from enough nodes, you know that you're not well connected, you're not timely, you're faulty, you should become passive. That's the pooling mechanism. So that's essentially pistis. I'm going to go back to the crux of why it works in a minute. But before that, I just want to mention again that, as always, we want to make sure that we want to make sure that the system works. And what does it mean here? We want to make sure that not too many nodes will become passive, because if too many nodes become passive, then the system is not going to be live anymore. The system is not going to work anymore. The system is not going to achieve anything anymore. So this is an evaluation that shows that even with a high rate of message losses, then the nodes still stay active and don't become passive. So even if you have lots of faults in your system, then the system still keeps working. So even not until rates of message losses of about 0.7, 0.8, not before that. Before that, system acts well, and after that, the nodes will start becoming passive.
And how did you come? Where do these numbers come from? Is this did you do an experiment? Or?
Yeah, so this is done through evaluations. Oh yes, I didn't mention that. So this was again evaluated. So this was written in C++ again. I like C++. But this wasn't done.
You do?
I do. Yeah, I didn't tell that to the students, but I do tell them. Anyway, so yeah, so this was implemented in C++, but the evaluation was done in the good old days when we're using simulators. Now we do our experiments on AWS. At the time it was done using Omnet++. We don't do that quite anymore, but yeah. All right, so switching gear a tiny bit again, talking a bit about verification. So we did a lot of work on verification over the last few years. We developed a number of frameworks to verify distributed systems. All of them were done in this prover. So Belisarius was a system that we developed to reason about BFT-SMR protocols in particular, and we proved the safety property of protocols such as PBFT, SM, other protocols using Belisarius. And then we moved on to hybrid systems. So we beefed up Belisarius so that it can handle those trusted components, can say something about, we can verify something about those trusted components. That was Aspalian. All in the spirit of Byzantine stuff, as you can see. Right. And more recently, what we did was take those frameworks and start verifying timeliness properties as well. So this is essentially the crux of the safety of pistis. So why is pistis timely? The way pistis works is that you have a node here that broadcasts a message, and then once it has received enough replies to its broadcast message and is still active, not passive, it will deliver the message. And after that, it will run this deliver phase. Because this deliver phase runs for this time period 2t, we can get the guarantee that we're going to have a quorum of, we're going to have a collection of 2f plus 1 nodes that will deliver the message during a time period t that overlaps with this 2t. Then that's essentially what we do with the pushing mechanism. Then what we do with the pulling mechanism is that if we have any other correct node, pj, pi is the node broadcasting a message. If we have pj, another correct node, how do we know that this correct node will deliver the message in a timely fashion? Well, because it's pulling messages, and we know that the node will run this proof of connectivity pulling mechanism, and it will pull at least from one of the correct nodes in this collection of 2i+1 nodes. It will pull the message that was broadcast by pi. And this is done by t within t plus 2t within this time period of t plus 2t. And that's how we can prove the timeliness property of pistis, which was done which was done in an extension of Asphalian and Belisarius. And that's all I want to say about this work so far on the verification, design and verification of distributed systems that we've done so far. So we worked on Dionysus, which is a hybrid streamlined DFT protocol, the first that was developed. Pistis, which is the first suite of reactive real-time DFT protocols. And we were actively verifying those protocols and now working towards verifying not the regular safety protocols, agreements, but also properties like timeliness. Thank you.
Can you say a little bit more about the formalization? So how do you formalize the protocols? Are they message traces of messages?
Yeah. So you have two main models out there. You've got the distributed, I mean, the two of them come from Lambo, as everything has. You have the distributed snapshots, which says that it's you essentially have a state machine where the state is the collection of states of all the nodes, make a step, transition to a new world, and so on. And then you have those what we call event orderings, which are based on events happening at different nodes. And then you have a partial order of those events. And from those two models are actually equivalent. They have their pros and cons. People typically use the distributed snapshot model, but from both of them, you can indeed extract traces and prove properties.
The second is event traces.
Both of them actually, from both of them, you can extract even.
What did you finally do in Coq?
What we did in Coq was verify. Okay, so with the distributed snapshot, one says you have your world that contains all the states of the nodes. Is that okay?
Yeah.
Okay. And then you take a step, and you have your messages in transit. You deliver one message, you take a step, and you output more messages. You take a step. For example, is in a new state. You again do the same thing, deliver a message, output new messages, get into a new state. That's the state machine. That's the distributed snapshot model. The other one says that you have a bunch of events happening, and you have a causal order between the nodes. And in both of them, as you can imagine, you can always extract traces from those.
But on the left, it's a set of traces then the model basically of these states.
Yeah.
Okay. And the right is event structures.
And the properties, your question was about what you actually proved.
No,
More a little bit how the model in Coq actually looks like.
Yeah, so our model in Coq, we actually initially went for this one. I eventually had another version implemented for pistis of this model. But it doesn't quite matter which one you use because in the end you reason about again those traces and they could be extracted from such a model or this model.
Okay, so reason over traces and trace sets.
Yeah.
Okay.
So for example, for safety, you want to say that if this node decides some message M1 and this node decides some message M2, then you want to prove that M1 is equal to M2. Why do we get this? because you can trace back the messages to something, to a point where you have a node that sent both M1 and M2. And this node was, this is horizontal, M1 and M2, and this node was correct. So, right. This node was correct. Somehow managed to send two messages that are different. That's not possible. Contradiction, the system is safe. Yeah. And you can do this, but you can do the same thing. Did I target the wrong audience? Should I have to?
No, I think it's a big.
You have a very challenging audience.
Yeah.
Potentially a couple of people here that are hardcore Isabel users.
Yeah.
And a couple of people that are more on the machine learning side and data science side of things. So you did a very good job.
Okay.
I have another question. So the people, the blockchain people, they claim that they can reach consensus with would be only 50%, so 2K.
Yeah.
2K participants without needing a trusted component.
Yeah.
So how
Like,
so what's the drawback?
For example, the proof of work.
Proof of
yeah,
work, yeah.
Kind of stuff, yeah. I mean, those are completely different systems. So yes, they don't rely on the same. Those systems, they rely on this property. You will always see this diagram of they collect quorums of 2f+1 messages. If you get a quorum of 2f+1 messages for M1 and a quorum of 2f+1 messages for M2, at the intersection you have how many nodes? F+1, right? You have at most F40 nodes. That means that you have at least one correct node here. This node cannot have voted for both M1 and M2. So it's based on those quorum systems that Daniel Malki and Daniel and other people worked on. And that's where this magic number of 3f+1 nodes. It's more than the majority for that, and that's where it comes from. But yeah, so the longest chain proof of work or also protocols, they don't rely on those quorum systems.
I mean, the advantage of these ones are then that they are far more.
It's deterministic. One thing, it's deterministic, right? So you get a deterministic property.
Okay, yeah,
Yeah.
that's
You just cannot fork, right? As opposed to the other systems where you can fork, and you get a probabilistic property about your.
you get hard guarantees. I think
Yeah.
in the other one you only get probabilistic.
Yeah. The only thing that you can do is this. This is well. This is just not possible. Just. So pros and cons. You need more nodes, but stronger guarantees.
And what was the property again, which you verified for your for the last protocol
So the one that we verified
in COG?
in COG here is this one time, yes. And so it says that if you have, four nodes, and one of them will broadcast the message. Then at time, so this one will broadcast the message at time t. Then you know that all the other nodes will broadcast the message between t and t plus t. And so they will. So this was the time when the message was broadcast, and they will deliver before this deadline. And that's the property that we proved in code.
This is discrete time steps here.
Yeah. And so something that I had mentioned is that this is all probabilistic, even though the model captures some form of probabilities, because we start with the model that says that the nodes will, the messages will be received with high probability within some time bound. So
So you verify the property you verified is a probabilistic property.
No, this is actually a deterministic property.
Okay.
Even though the model captures some form of probability, probability, the properties are all deterministic. So the properties I've shown you before were all deterministic properties.
But your reasoning framework, does it allow for probabilistic?
No. Yeah, so that's something that I actually tried before in COP again, and it didn't work. So I was using this, like, we can talk a bit more offline about this, but I was using this library which was very not compositional, and after a bit I just gave up on this because it wasn't just working. You couldn't compose your proofs and get nice probabilistic properties. Or at least I couldn't make it work. So yeah, what I wanted to do is not only prove that. So this is saying that all the correct nodes will deliver by that deadline. Okay, but what about this picture I showed before? What about this? Can we say something about the liveness of the system? The fact that with high probability, the nodes will stay correct. And indeed, if they stay correct, they deliver by some deadline, but will they actually stay correct? And this is a probabilistic property. That's what I wanted to prove in COC, but gave up after a bit.
But what property, so of the thing you proved, you said something is probabilistic, not the property, but the model for.
The model is probabilistic, yeah. Because so the model is, let me go back.
But then how could you then prove this non-probabilistic property?
Yeah, because all the, so even though, so the
It's blank. I mean, the other one is blank.
no, that's fine.
Maybe just.
So it's a new building that I forgot to put some. Or you have to bring your pen and your eraser. Or you have to write everything on the slide. Or you have to have a tablet, which is what you put in. Right. So the model says if you send a message at some time t, then with high probability, it will be received by time t plus some d. So this is a probabilistic property about the model. But what we are verifying is that if a node broadcasts a message, then at time t, then all the correct nodes will deliver the message by time t plus some delta of d. They will deliver here, and those nodes are all correct. That means that they didn't become passive, and in the end, that means that all the messages were indeed received by within the right amount of time. So in the end, it didn't quite matter. The late messages don't quite matter in those proofs because we only reason about correct nodes that achieve something by some deadline. So they have, if they become passive, if they miss the deadline, if they don't get enough messages by some deadline, they become passive.
Okay, yeah, I get the idea.
Yeah.
Totally unrelated to that discussion one. I somehow have the feeling that requiring a trusted component like the Intel trusted component is already a pretty strong assumption.
Yeah.
And those components are pretty powerful.
Yeah.
They provide much more cryptographic functionality, for example. Are you working also on thinking about how to simplify those protocols, saying every machine that we have these days has these powerful trusted components? Let's make use of all the features they have.
Oh yeah. So that's something that has been done. So what I would say the worst case scenario is, or the simplest option is to just run the whole thing inside IntelliSGX, and then you don't need to do any replication, right? Because the code is structured. But then the thing is that most of those, then you have to rely on the correctness of those trusted components. And we know that SGX was actually broken. We used SGX because
Yeah, but that you have already if you only use it for signing.
Sorry?
If you only use it for signing or for the trusted counter, you already trusted that it's not broken.
Yeah, yeah.
And that your cloud provider doesn't give you a software implementation of it in your VM and all those kind of things.
But our point is that here, sure, we use these high-powered IntelliSGX, those high-powered IntelliSGX components that provide lots of features and can actually run the whole code. But this was just for the evaluation. Our point is that many computers will not have IntelliSGX running. You have an IMD machine, it's something that will have IntelliSGX. So, but many machines have TPMs, and you only need something like a TPM for trusted counter. So those systems, you can run them, and now you have all those devices that are created. You have those keys that can run also trusted computations and but very simple trusted computations. People are working on those small devices that can run very simple computations. And the point is that those protocols could be run in an heterogeneous system where you have different components that different machines that have different trusted components, and not all high powered computers.
Yeah, I think thanks, Vincent, for the talk. I think we will still enjoy a little coffee if there are other questions. You can ask Vincent now. Okay, yeah. Then I think we are done. Is Jogo still online?
No, let's see. I think we can just stop the yeah, so I've got this issue with Zoom that now it's I can't make, so yeah, but I need to just close Zoom. I'm sorry.
I mean, yeah, just close Zoom.
Yeah.
Kill Zoom.